Okay, so other than that, this is stuff that you're familiar with now. We just reviewed it a good bit, so I'm hoping that it's sticking with you. So I want to show you how do we relate this to a reaction. So I'm going to scroll all the way back to that thing that I just showed you. I'm going to skip a couple of these problems for now. This thing, nope, yes, this thing. So this is a bigger, badder flow map of exactly what I just showed you. It's really little, so I'll have you write down some of these things later, but I want you to just see that what I've done is, like, maybe I'll give you something with particles, like atoms. I'll say atoms of a reactant, and then have you convert from atoms of the reactant to moles of the reactant, that reactant called X. Do you know how to convert from atoms to moles? Yes, using what? Avogadro number, right? So if I wanted you to go from moles of one reactant to moles of one product, then that is called a mole ratio. And the mole ratio is simply a coefficient. That's it. So what do you need before you can find coefficients? A balanced chemical equation. So you're seeing how we're pulling together old stuff with reactions that we did last week. So you need a balanced chemical equation. And so a mole ratio is literally taking a coefficient of one reactant, a coefficient from another product, or vice versa, and putting into a fraction, and then we're going to use that to finish out the problem. I might ask for you to figure out how many grams of a product is going to be made. Well, once you get to moles of that product, how do you get to grams of that product? How do you get from moles to grams? Molar mass. That's it. So there's multiple pathways to take, but if you know the relationship from moles to any of those, then this process is just so easy. It's just canceling units. So we're going to go through an easy example first with cupcakes. Who likes cupcakes? Hold up. Let me show you my cupcake example. I'm a little all everywhere today. Okay, so here's my example. Baking with stoichiometry. A cupcake uses baking soda to make them rise, so they are light and fluffy. The reaction this reaction creates small pockets of air in the cupcake to give them their texture. This is the reaction. Write down this reaction. Does this reaction look familiar?
Write this on the separate sheet.
Write this on a separate sheet of paper. There's no way in Hades you're going to fit it on that little sheet. Where have you seen this reaction before? The lab. You were baking with stoichiometry, except without baking. You were just making air. Woo! Pat yourself on the back. You made air yesterday. Woo! Or day before. Okay, so we have this reaction. If I were making the cupcakes, to make them perfect, you have to create 50 milliliters of carbon dioxide per cupcake. Okay, so what are we seeing? First of all, you have I'm going to put CE, chemical equation. What's not there? Balance. So let's balance this before we even start reading the rest of the problem. I made this long so you would realize the importance of writing down what we need to write down. The only thing we need to do right here is balance. So tell me what I got to do. What's that thing? Sodium bicarbonate. Right. Okay, sodium bicarbonate gets a 2 in the front, and then what else? Or is it good? I think it's good, right?
No.
2 NAs, 2 H's, 2 NAs, 2 H's. 2 carbons. There you go. 2 carbon dioxides. And 6 oxygens all the way. There we go. Okay, BC, done. You got it down. So as for reading, I want you to write down the important pieces of information. So what's the first important piece you see? 50 mils of what? Carbon dioxide. So write down 50 milliliters CO2. That is a given. That is a piece of given information. Per cupcake. So just keep that in mind. This is per cupcake. I'll not even write it just to keep it in mind. Per cupcake. To create just the right amount of lift. So what's my question? You can see it in the next sentence. What am I looking for? Okay, so what mass? Question mark. What's the unit for mass? Grams of what? Baking soda. NaHCO3 is baking soda. Sodium bicarbonate is baking soda. Okay, so it's required per cupcake to create this much gas at STP. So this is one more piece of information that I'm just going to write maybe right here at STP to remember that there's an important conversion factor at STP. Okay, so I'm not going to read the question anymore, but I do need that BC, so I'm going to leave my BC right here in front of me. So I'm using this, and I have this given information. Whenever I start a stoichiometry problem, I always start with the given. Well, what one piece of information is the given that's important? 50 mils, right? So if I have 50 milliliters of CO2, your thought process should say, I have milliliters. I need to get rid of milliliters. How do I get rid of milliliters? So what do I put on the bottom? I am not in liters yet though, right? I got to get out of milliliters 2 liters because you know that you want to use the 22.4 liters per mole, but we're not there yet. Yeah. How do I cancel milliliters though? I'm converting to liters, so 1 liter contains how many milliliters? 1,000 milliliters. King Henry died by that stuff. Okay, so cancel out your milliliters now. Cancel out your milliliters now. So this is CO2, by the way. I'm sorry. Make sure you write your identity because we're getting ready to stop talking about CO2. We're going to start talking about sodium bicarbonate, but I don't know unless you tell me. Yeah. Yes. Pass that. Okay, so now we're in liters of CO2. There's only one way to get out of liters. How? Give me the moles, right? So what goes on top? 1 mole of CO2. What goes on bottom? Liters of CO2. Good. Because I had to cancel liters, so I put liters to liters. The more participation I get, the better the class is. So keep going. I'm in moles of CO2. This is where I need to stop. I'm stuck at moles of CO2. But it's not the CO2 that I care about. It's actually the questions referring to sodium bicarbonate. So this is where you get to look at the BCE and tell me their relationship. What is the relationship between this and this? 2 to 2. For every 2 moles of CO2 that I make, I require 2 moles of sodium bicarbonate because the ratio says so, the BCE says so. So what was that term I just used to describe what those 2 numbers mean? Mole ratio. It's literally coefficients right on top of each other, and you put mole next to it. So why did I stop here at moles then? Because I need moles to get to the ratio, because the ratio is called a mole ratio. So at this point, I'm actually going to look at the BCE and go, okay, I have 2 moles of CO2. I'm putting on the bottom. So 2 moles of CO2 created for every, what? 2 moles of sodium bicarbonate. Good. So you could put 1 to 1, but I'm literally copying the coefficients and putting them in the fraction. So this is the step. This is the bridge. This is the crossover from reactants. From one chemical to another chemical, one compound to another. And that's great because who cares about CO2? The question's not asking about it. We're asking for grams of sodium bicarbonate. Notice I did not reread the question. I have my grams right here. Now I'm in a good place. How do I get from moles to grams? Molar mass. So calculator, tell me what the mass of sodium bicarbonate is. Get your periodic tables out, hopefully, because you don't need to be memorizing that stuff. Go for it. 84.008 grams of sodium bicarbonate per what? What gets right? What's in the bottom? 1 mole. And I can't fit this, but I'm going to squeeze it. Sodium bicarbonate. Whew. Okay, so then reflect on this. Did we get to our final unit that we wanted? Yes. Moles of sodium bicarbonate canceled. Grams of sodium bicarbonate have been attained. How do you actually calculate this, though? We just have math set up. We haven't calculated a darn thing yet. Tell me how to do this in your calculator. And as you do it, do it in your calculator as you tell me.
Divided by
1,000. Divided by 22.4.
Times 84.
Times 84. 0.008, since I had a very specific. And you get 0.1875 what? Grams of sodium bicarbonate. Per cupcake, right? Per cake. Because that was the question asked for. Yeah.
What happens to the second mole of sodium bicarbonate? Because when you copy it down, you just put 1 mole.
It's because I don't refer to the number when I'm copying it down. I'm only referring to the unit. And the reason I do that is because I've already accounted for the number on which they react here. So if I doubly do that, I undo what I've already done. So I put a 2 there. I'm actually saying if I put a 2 there, that would say 1 mole of sodium bicarbonate is used to make 2 moles of CO2. But the reaction says different. The reaction says I'm in a 2 to 2. It's like a new situation every single conversion factor. You're only considering one thing at a time. So you're like, okay, I got to get to liters. Okay, I've got to use the liters to get to moles. Okay, I've got to get the mole ratio. And then separately, if I had one of these, how much would it weigh? If you did put 2 of those moles there, you'd have to double your mass. But it would come out with the same answer. Don't do that though. Let's try not to. Otherwise though, we have our answer, 0.1875 grams of sodium bicarbonate per cupcake. Ooh, that's not that much, right? If you're baking, that's not that much. So if I wanted to make 2 dozen cupcakes though, like most people don't make 1 cupcake, that's a lot of willpower right there. If you want to make 2 dozen cupcakes, how would you get the number of the grams of sodium bicarbonate you would need? So multiply by 24. So that's easy, but I want to show you how you actually did it in your head with stoichiometry. You said 0.1875 grams of sodium bicarbonate per 1 cupcake. You said that was a conversion factor. That's what you just did. And then you said, okay, I need 24 cupcakes, so I multiply by 24 cupcakes. And what cancels? Cupcakes cancel. And you get, that times 24, which is exactly what you just told me to do. What is that? Good job, guys. 4.50 grams. Yeah. Okay, so that's more reasonable. So if you were trying to make do a recipe. If you were trying to cook something, then you'd actually weigh out that many grams of sodium bicarbonate to get the perfect recipe, the perfect cupcake. Yeah. Air file. There you go. Okay. So let's keep going. We still have our BCE. Using the same BCE the whole problem. Using that mass, so this mass of sodium, baking soda, how much total sodium oxide would have been produced? So if I started off with that grams of sodium bicarbonate, and I wanted to get to how much, what do you think much stands for, what unit? Grams would it be produced? Okay, so what's our given? Sodium bicarbonate, okay? And my question? What's my real question? Grams of what? So question, sodium oxide. All right, you guys have the BCE in front of you. I don't. Mine's way up high, up on the board. The BCE, balanced chemical equation. You have that in front of you. Okay, so you tell me. I'm in grams of sodium bicarbonate. I can't do crap with grams. Get me out of grams. Give me the moles. How do I get to moles? 1 mole on top and, HCO3. What was that molar mass? Remember, you're canceling grams here. 84.008 grams of sodium bicarbonate on bottom. All right, everybody is writing these problems down. If not, you will have nothing to look back at for help for homework. Yeah. So grams of sodium bicarbonate are now canceled. Now we're in moles of sodium bicarbonate. Ain't nobody care about sodium bicarbonate. What do we care about? The other thing, which is called sodium oxide. What is the relationship between sodium bicarbonate and sodium oxide? 2 to 1. So I'm going to scroll all the way back up. You just told me 2 to 1 because of the coefficients, right? But which of those would go on top of my next conversion? Why the 1, Jacob?
That's what you're trying to do.
You're trying to get to that. So that has to go on top because this one has to cancel. So I'm looking at there 2 to 1. So remember that, 2 to 1. So then I'm down here. 1 mole of sodium oxide, because that's what it said in the BCE, was the 1. So I'm just going to put BCE here so you remember that's where we got it from. And then 2 moles of sodium hydrogen carbonate or bicarbonate on bottom. So that gets us out of this reactant into this product that we desire to know some information about. So moles of sodium bicarbonate cancel, baking soda. We're in moles of sodium oxide. What was my question again? Grams. How do I get to grams? Calculate. Okay, 1 mole of sodium oxide goes on bottom because I need to cancel sodium oxide. And in your calculator, tell me what the mass of that is. I believe you. 61.98 grams of sodium oxide. So what did you do in your calculator? You just added 23 plus 23 plus 16 because that's the mass of each of those elements. Okay, then you're like, well, last scratch. Moles of sodium oxide. Moles of sodium oxide? How many grams of sodium oxide? Yes, that's what I asked for. And then you calculate. And what are you doing in your calculator?
4.5 divided by 84.
0.08,
Divided by 2.
Divided by 2.
61.98.
0.98.
1.66.
That's it. So this 1.66 grams of sodium oxide is created. So why would a baker want to know how much of this product is made? Because yeah. No, you go. It's good. Okay, well this is staying in the cupcake, right? So this is a product. It's not a gas because we made sodium oxide, water, and carbon dioxide. The carbon dioxide is coming out, it's lifting the cupcake, it's making it look kind of light and fluffy. This is staying in the cupcake. Some chemicals in high amounts are somewhat toxic, right? They also make things pretty bitter sometimes. If they had left too much of that in the cupcake, it would taste like poop. Okay, it would taste awful. So they have to make sure they've just right enough to make a lift, but not too much, because then it would taste really horrible. We've all had horrible cupcakes. No, there's no such thing as a horrible cupcake. So they have to make sure they have just the right amount of everything. Yeah.
Can you explain why we started in grams and then ended in grams?
Yes. So my question, the question given that said using that mass of baking soda. So I gave you mass originally, but mass of reactant A, of one thing. And as the process happens, as the reaction happens, I want to know how much product I make. So I asked for how much product I made, so I asked for how much mass I made of the product. So we now know how to get from grams of A to grams of B through a chemical reaction. It's actually, it's more like giving you something in grams and then asking for something else in grams is more realistic than not giving you something in moles, because you're like, what is a mole still? So it's more realistic to ask that way, because it's like a baking example. Because they don't have scales that say moles, they have scales that say grams. Okay, last question, or no, how much is in each cupcake? If that's how many grams are in all 24 cupcakes, what would you do to figure out how much is in each cupcake?
24.
Divide by 24. Okay, I'm not going to do that. You would divide, if that's total, each cupcake would be divided by 24. Okay, so last one. How many molecules of carbon dioxide are made in each cupcake using the information given initially? So what information was given initially about the carbon dioxide? Yeah. Because it's asking about carbon dioxide, right? What was given initially? 50 milliliters. So 50 milliliters of CO2. That's still our starting point. That's our given. What is our unknown? What is our question? So question is molecules of CO2. All right, this is nice. This is a nice one to end on, because I'm in CO2 and I'm in CO2 still. Do I need a BCE for this one? No, because I'm not looking at a relationship between a reactant and a product. I'm looking at just carbon dioxide. This is stuff we did a week ago. Okay, so start me off. What do? Get it to liters. So 50 milliliters to liters means what? 1,000 milliliters on bottom. 1 liter of CO2 on top. All right, I'm in this useless unit of liters. I hear it. Say again. 22.4 liters goes on top or bottom? Right, so 22.4 liters goes on bottom because I need to cancel liters top and bottom, and 1 mole of CO2 goes on top. Okay? So far, so good. Milliliters of CO2 cancel on top and bottom. Liters of CO2 cancel top and bottom. Moles of CO2 now need to be canceled. But go where? Right, into what? What's that unit? Going to molecules using Avogadro's number, right. So that's when you have to stop and think for a second. You're like, okay, I'm in moles. I know I can do everything with moles, but which specific relationship do I want? I want to get to molecules, and there is a relationship there. 1 mole of CO2 contains 6.022 times 10 to the 23 molecules of CO2. How many molecules is that? Don't do mental math. You have a calculator. It's all good. Yeah, specifically. Go for it, Amy. 0.34 times 10 to the 21st molecules of CO2. So that little 50 milliliter sample, think of how big 50 milliliters is. It's not very big. How much? It's making that many molecules of CO2. Huge amounts, yeah. Yes, you do. And I was trying to not for now because we're learning new concepts. So there's a couple in here that I would have to consider. And I would have actually, I just typed this example up, made this up before class to give you a better example than the boring chemistry ones. So it should have been 50.0 to give us more sig figs. Because I make very accurate measurements in my baking. Okay, 50.0, not just 50 milliliters.
Yeah.
Big difference there. Okay, so who feels like they understand reaction stoichiometry on a scale of 1 to 10? 10 means I'm a boss, 5 means I'm half boss. One's like, did I just, what just happened? I didn't see honest answers. Okay, Caroline's like, what? 1? Okay, so I'm going to maybe do one more with you. That's actually in your student practice, and then I'll let you guys practice by yourself, okay? So on your student practice, I have a lot of different notes, but if you got it, then I'm not going to bore you to tears with notes. I'm going to do the one in the student practice ones, which is y'all's. I have jokes for you too. I'll go back to jokes. Okay, so on yours, do you see where it says, consider the decomposition of potassium chlorate? Where it says student examples. Student examples. So it says you tried lecture practice. Sorry, it says you tried lecture practice. Potassium chlorate. You see that? It's in the lower right-hand quadrant.
Oh, yeah.
Okay. Yes. So this one's going to guide you through a bit more technical ones. Okay. So you guys participate. Help me out here. Tell me what the reaction is. The decomposition of potassium chlorate. And if you need to pull out your foldable on how do chlorates decompose, might be helpful right now. I hear you. What's up? Huh? What's up? Okay. KClO3. Yield. So, whoa, what? This is a chlorate. You're thinking carbonates make carbon dioxide. Chlorates make oxygen because we can't make chlorine because then we die. Okay. Oxygen and KCl. Right. This was the gummy bear one. They made oxygen and then they combusted the gummy bear. Okay. Okay. So balance.
I'll put a 3 in front of the ACL
Or the O. Okay. Yeah.
Sure. And then put a 2 in front of the KCL.
And then anything else?
And then put another.
Oh, I got you. Reading your mind and stuff. That's all good. So every single question you do with reaction stoichiometry. Step 1, BCE. Step 2, ID the givens. Okay, but we don't have givens just yet. All right, so we got a reaction. First one is, what are the mole relationships between potassium chlorate and oxygen gas? What is it? So potassium chlorate first. Potassium chlorate first. So 2 moles of potassium chlorate. Where did I get this 2 from? The BCE right here. Over 3 moles of oxygen. Did I have to write it this way? No. It depends on what the reaction call or what the stoichiometry calls for, but it could have been flipped. It depends. But I have a mole relationship because I took the coefficients and I put them as a fraction. Step 1 is easy, right? That was the first one. Next, question says, if 75 grams of potassium chlorate decomposes, what is the mass of oxygen gas produced? So I want you guys to pull out the given. What's the given here? Shout it out. Yep, 75 grams. 75 grams of KClO3. Write the identity with it. Okay, what's our question? Shout it out. So give me units for that. Grams. So question is grams of what? O2. Okay, so that's our end unit. That's our desired unit at the end. All right, so I can't do anything with grams except go where? Moles. It's a known step. So what goes on top?
1 mole.
1 mole of KClO3. And then what goes on bottom? What's the molar mass? Do, 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 do. So this is a very dynamic process. You're pulling a calculator, you're going for it. It keeps you engaged, people. Today, I already know who I'm giving more money to for participation. So I appreciate your enthusiasm. 122.55. Yes, what's up? I don't have any more right now. Use your phone for now. Okay, it's just a little bit more difficult. Okay, so then 122.5 is the molar mass by adding those up.
So you can't spell multiplication.
Okay. Now, where do I go for moles of potassium chlorate? Mole ratio, because I can't, once I'm stuck in moles of one thing, I can only go to moles of something else, and that's what I need to do because I need to get to oxygen. So I'm looking at the, okay, but do I write it like this? Why? Because I need oxygen on top. I'm going to oxygen, so it's got to go on top. So tell me what I have here.
So you have 30 mole O2.
Uh-huh.
Then 2 mole HCl.
And where do these numbers come from again? Coefficients, right, from the BCE. So our question again was grams of O2. Okay, so I'm in my moles of potassium chlorate, top and bottom can cancel. Next.
Then
I go back to grams, right? So I hear you telling me to do what?
1 mole on top.
1 mole of what on bottom? O2 weighs. How do you know that? Because you know how it's 16 times 2 is. So smart, people. Okay, grams of oxygen. Calculate.
so now you got 25.
I got 29. I think you forgot to divide by 2. So why are we going back to grams? I heard that question. Why are we going back to grams of oxygens? Because it asks for the mass, right? And it's not the same story. If you're going to grams of something new from grams of something that was given to you previously. So it's like saying, it's kind of like saying, I don't know, I'm going to make up this example. If you take in, a sandwich, okay? You eat a sandwich, how much energy can you make? It's based off of your metabolism, the chemical reactions inside, but it's putting one thing out and getting something else out. And that's grams of oxygen, by the way. Okay, so I think I've got one more on here, part C and D, and then I'll stop for now. Yes, ma'am?
I have a question on the problem we just did. For that, how do you know whether to multiply by 3, divide by 2, and then calculate it?
You have to do both. Multiply by 3 and divide by 2. I usually just put in my calculator times 3/2 in parentheses. I use parentheses like crazy. So I do like 75 times 1 divided by 122 in parentheses times 3/2 in parentheses times 32. Because I have this fancy calculator. So let's do that. Okay, keep it going. Let's do these last 2 and then I'll leave you alone. Let you guys do some of your own practice. You have less to do for at home. So what's your first step? Let me get somebody else. Let's go with Natalie. I already have that on my previous. This is a continuation.
Oh, so you pick your given.
What's that? And what's our question? So question is liters of O2. That's you. All right, so Jake, tell me where to go from here. I'm starting with grams.
And then you get to moles.
Okay, so 1 mole on top, what goes on bottom? Which we all know is what? 1 to 22.5. You just wrote it down previously, right? Okay. Jack, tell me the next step.
You have to go from moles of potassium chlorate to moles of oxygen.
Right, and you guys have your BCE, right? It was 2, I'll just rewrite mine real fast, to 2 to 3. Okay, so what's that ratio?
2 to 3.
So what goes on top?
The oxygen.
So what goes on top? 3 moles of oxygen on top and
2 moles of
on bottom. Good. So that 2 to 3 came from strictly at looking at the coefficients. Okay, so I'm just going to go ahead and cancel these as we go. Grams of potassium chlorate, top and bottom. Moles of potassium chlorate, top and bottom. Now I'm in moles of oxygen. I want to get to liters. Give me there. Right, so where does 22.4 go? So it's 22.4 liters of oxygen per 1 mole of oxygen. And you're assuming this is at STP. I haven't told you any other reason not to believe that, so assume STP. Yay! So moles of oxygen cancel. And what do you got to do now? Multiply it out. And if you don't have a calculator yet, your heart is going to start to hurt. Your brain's going to start to hurt probably more than your heart.
14.67.
I believe you. 14.67. Do we concur? Yes. 0.67 liters of oxygen. And for sig fig purposes, the only thing you're considering is there are 3 sig figs here. So then what would this round to? 14.7 liters of oxygen. Okay. Last one for now. Question is what? Grams of, which is, spell it out. KCl. Fluoride, right? You gotta pay attention to that ending. So now we're going to grams of KCl, produced from the same amount of potassium chlorate as in part B. So how much potassium chlorate did we have in part B? 75 grams. Okay, so what do we call that? Our given. Okay, so 75.0 grams of KClO3. Kathleen, tell me where to go from here. Right, so moles go on top, and what goes on bottom? A little repetitive, but we've seen that number 3 times now. Okay, so that makes life a little easier. So grams of potassium chlorate go away. I'm in moles of potassium chlorate. Who cares about potassium chlorate? What do we care about? Potassium chloride. Glenn, tell me where to go from there. I don't have my BC up here. I'm sorry. It's high. It's up there. You have it in front of you though. Right. What's the ratio? 2 to 2. So we're looking at potassium chlorate and potassium chloride, potassium chlorate. So this one's going on top. This one's going on bottom. It so happens to be the same number, which makes life good and good, but we're all here. 2 moles. KClO3 on bottom, because that's what the BCE says, right? And then 2 moles of KCl on top, because that's what BCE says. Okay. Danielle, tell me the last step. Yeah. On bottom, right? Because I got to cancel it. And on top, what's the number?
74.55.
Say again?
74.5.
74.55 grams. Okie dokie. Moles of potassium chlorate go away. Moles of KCl go away. We're in grams of KCl. Yeah.
How did you get the 75?
This was, I had to look back at part B to get that. We had to scooch back. All right, so you guys tell me what you get when you get there. 642 grams of KCl. How many sig figs should we record that to? How many? 3, because we have 3 sig figs here. This is the ratios are not measurements, so they don't count. This is a number that's pretty long. This number's pretty long, so that's our limiting one. So then round it. 0.6 grams. Okay, so what I want you guys to do is for the next little bit, work with a partner on practice question 2, and if we can do practice question 3 in class, that'd be great. So, and I will put answers up as you go. Okay, so this is going to make sure you have time to work on problems that well tonight. You won't do any lecture bombs tonight. Yeah. potassium weighs 39.10. Chlorine weighs 35.45. Did you get it right? I just believe that. Alright, you guys are doing practice 2 and practice 3, and if I need to, then I'll do practice 4, but you guys have practice 2. Alright, if you need to get up and move, get up and move. You've been sitting for a while. You can stand up, go to your last station, it's fine. Just go to